Okay, so tomorrow's lab won't be in 101 because I think it's occupied. So I have an email out to the other person who makes the arrangements. And my order of preference was this room, and then that room, and then 301, and then ICN. So surely one of those. So I'll push out on Twitter, send an email, and post on the door. Okay? So we're going to pick up where we left off. In kind of getting ready for tomorrow's lab, you're going to be drawing Lewis structures. And one of the things about Lewis structures is once you have them drawn, if you count, see the heading of that, the first column, if you count for an atom, you just have to go one atom at a time. You pick an atom, if you count sigma bonds, not pi, sigma bonds, because remember if you have a triple bond, it's only one sigma bond, right? Sigma bonds and lone pair electrons, then you know what we call its shape around that atom. Lone pair electrons and sigma bonds. And if you have two things extending from that atom, we said that the electron pair geometry is going to be linear. If you have three things, we said it's going to be trigonal planar. If you have four things, it's going to be tetrahedral. And then what's going on behind the scenes is actually this third column. In order for that number of sigma bonds and lone pair electrons to do its thing, you have that atom undergoing sp orbital hybridization, sp2 and sp3 orbital hybridization. You're going to want to know all of that. And then last but not least, that other column is what is the bond angle. Okay, so you have 180 for a linear, 120 for a trigonal planar, and 109.5 for tetrahedral. So you're going to want to know that. And I have some pictures to kind of reinforce what that looks like. So here's a figure from your textbook. The first column, the electron groups, actually that corresponds to the first column on the previous table. Notice what I said is you add sigma bonds, that would be their bonding groups, and lone pair electrons. Okay, so the shape is linear. The bond angles is 180, and an example of it is carbon dioxide. So like when they say an example is carbon dioxide, what they are doing is picking on the carbon atom. They're counting sigma bonds. We have a sigma there, and we have a sigma there. Remember that the second to arrive is a pi bond. Okay, so you count only sigma bonds. That's why we say around that carbon atom we have two things. Okay. The next two actually kind of go together. In one case, you have 3 sigma bonds, no lone pair electrons. In the other case, you have 2 sigma bonds, 1 lone pair electron. In both cases, they add up to 3. So you have 3 things extending from that atom. The atoms here is the central carbon atom there and the central sulfur atom there. So the carbon atom has 1, 2, 3. Okay. Remember that that other one over there is pi, and it doesn't count. This is kind of what we talked about on Monday. And then over here for this central sulfur atom, it has 1 pi, it has 1 sigma bond here, 1 sigma bond here, and then it has a lone pair electron. So just for that central sulfur atom, it kind of looks like this. This could be one of the sigma bonds to the oxygen. This could be one of the sigma bonds to the other oxygen. And this is the lone pair electrons around that sulfur atom. I got 3. We know that's trigonal planar, okay, and the bond angle is 120. So for the one structure up above it with the carbon single bond hydrogens and then double bond oxygen, this would be replaced with a double bond oxygen. But only the sigma bond is what makes its shape. The others, this last down here, okay, these are all, they add up to 4. And when I say add up to 4, I mean sigma bonds and lone pair electrons. So we kind of have a couple different combinations. We can have 4 sigma bonds, we have 3 sigma bonds, 1 lone pair electron, 2 sigma bonds, 2 lone pair electrons. By the way, we talked about this. This is the Lewis structure of water over here. If you look at the central oxygen atom, the oxygen atom in the middle, I'm counting 2 sigma bonds and 2 lone pair electrons. That's the 4 things that's giving shape around the oxygen atom. You don't look convinced, but now before I move on, I'm going to add one more thing to kind of what's going on behind the scenes. I'm going to take this row. Oh, maybe it's coming up. There it is. No, I guess not. I'm going to take the first row, and I'm going to call that SP hybridization. I'm going to take the next 2 rows. I'm going to call that SP2. And I'm going to take the last ones. I'm going to call that SP3. So, for instance, SP3 orbital hybridization, you have 4 things, whether they're sigma bonds or lone pair electron scattering. And these are all tetrahedral. Now, again, when I say tetrahedral, I'm just pointing to one atom and talking about the geometry around it. The electron pair geometry is different than the shape of the molecule, the geometry of the molecule. All right, so SP hybridization gives you 2 things that are going to scatter. Remember electron pair repulsion theory, repulse from the nucleus of the atom that's hybridized its orbitals, atomic orbitals, to overlap to make bonding orbitals. So SP2, we have 3 things scattering from that atom, 3 hybridized orbitals. In this case, we're picking on boron. Remember, boron is a crazy dude. It only wants to have, in its final Lewis structure, it only wants to have 6 electrons. So a lot of times it will just reach out 6 times like that. And then again, we have methane down here. Central carbon atom that's singly bonded to 4 hydrogens. Okay, so you count sigma bonds, I got 4 down there. You count lone pair electrons, I got 0. So of course 4 plus 0 is 4. So we're looking at SP3 orbital hybridization. So I probably should move my slides around because I think this is a good way to look at it. The whole repulsion idea, how far apart can they get, as far apart as possible. If you have 2 lobes with the green balloon, 2 balloons, okay, that's your linear. Okay, that's basically you have an atom that is extending 2 equal hybridized orbitals in just 2 directions, and the farthest they can get apart from each other is 180 degrees. The middle one, SP2 orbital hybridization, trigonal planar. The third one, SP3 orbital hybridization. That's the tetrahedral, 109 degrees. Now, for this course, we're not going to talk about expanded valences. I don't know if you guys remember in Monday's class we talked about octet, 8 electrons. Well, an expanded valence is where an atom says, I want more than 8, and it usually goes, I want 10, or I want 12. And in that case, actually, you come up with a different scenario. So this one right here, I might be having my slides coming up. So this is SP, SP2, SP3. That's what we're worried about. Expanded valences look like this, where SP3D, how exciting is that? And the next one is SP3D2, where actually, when you count the electrons around that atom that's right there, in the case of SP3D, it's going to have 10 electrons. In the case of SP3D2, it's going to have 12 electrons. How totally fun is that in the final Lewis structure? Okay. And you might be saying, well, how do these get a complete octet? And the answer is pi bonds. They don't count for geometry, but they count for giving it an octet. Okay, some more balloons. So, you know, in tomorrow's lab, you guys are going to be drawing Lewis structures, and you're going to be evaluating an atom for, It's hybridization, it's shape. Okay, and so this is to kind of reinforce that. If you have two things, and again, only thing you can count are sigma bonds and lone pair electrons. Two things will give you linear, three things will give you trigonal planar, four things will give you tetrahedral, five things would give you trigonal bipyramidal, expanded valence, sp3d, sp3d2 would give you octahedral, which again, so we're on the same page, we are only going to worry about these guys. I have a lot of slides. We are only going to worry about these guys. No expanded valences for us tomorrow. Okay, so it would look like tomorrow, or one of the skills, I guess I should say, like I said, is I need to pick an atom. So down here, do you see where I have picked an atom? Tomorrow we'll talk about a central atom. Central means the atom in the middle. Sometimes it's hard to find the atom in the middle. But I just want to answer questions about nitrogen in ammonia, in this Lewis structure. So hopefully you can count, well, it already says here, if you count sigma bonds, you got 3. 1, 2, 3. That's your 3 sigma bonds. If you count lone pair electrons, you got 1. So I have 4 check marks up there, 3 plus 1. So what's its orbital hybridization? It is sp3. And then what's its geometry? Tetrahedral. And then what would be the bond angle? 109.5. Does that work? And tomorrow, I think I'll remember. Every once in a while I forget to get them out, but tomorrow you guys are going to have not wooden sets, but you'll have little plastic models. Okay, so this is NH3. This is ammonia. Not to be confused with ammonium, right? Ammonia. So it's not contained in a plane. These lie outside the plane a little bit. This is tetrahedral. And this bond angle right here is 109.5, which I used to say that's a great call numbers for a radio station. There is no such radio station. Doesn't go up that high. Okay, so let's pick on carbon. Again, these questions can only go if you know what atom you're supposed to be asking about. So let's pick on carbon. So like you see, if we just pick up sigma bonds, we only have 3, because if you have a double bond, only one of them is a sigma bond. Remember, I brought these on Monday, and I said the gray things are sigma bonds, okay? The gray things are sigma bonds. Those pink things don't give shape to geometry or to that atom. The pink things we said were pi bonds. To get one pi bond, you need to have pink above and pink below, or pink above and purple below. Okay. So, all right. So I got 3. No lone pair electrons, 3 sigma bonds. So what's its orbital hybridization? It is sp2. And what's its structural geometry? Trigonal planar. I'll buy that. And so what's its bond angle? 120. And so tomorrow when you guys are working these, I'll kind of, in the lab background information, you'll have, I don't know how big it is, but you'll have that little table that has, the first column is either 2, 3, or 4, and the heading says sigma bonds and lone pair electrons. I'll be referring to that a lot. So basically, when you answer the first question, how many sigma bonds, lone pair electrons, then you have the whole row to fill out the other information. All right. So this is that structure. And this is a good example, kind of left to right. I mean, it looks like there's a 90-degree angle between those carbons and the double bond oxygen, but that's not true. According to electron-pair repulsion theory, those 3 electron domains will spread themselves in a 120-degree angle. So this is where you can take the Lewis structure on the left and kind of think of it, what it really does on the right. Now, granted, and we aren't going to do complicated molecules, but when molecules get more complicated, you can kind of dissect them like atom by atom to understand what they are. Okay, one more, or maybe one more. So this one, this is where you're like, well, what's the central atom? There's only 2 atoms. I don't know, pick one. So tomorrow we'll kind of have to struggle with that a little bit. But in this case, we're picking on chlorine. So if you pick on chlorine, it says I got 1 sigma bond right there, and I have a whopping 3 pairs of lone pair electrons. So here's where I go 1 plus 3 is 4. Okay, so what is its orbital hybridization? It is sp3. So you go back to that table, you go back to the bottom row, which says 4, and you answer all these questions. The structural geometry, it's tetrahedral. See, does this say not applicable? So notice that it's really hard to say what the bond angle is, because for a bond angle you need 2 bonds, a pair of bonds. And the electron domain, it has 1 bond and the other one's shooting off, you know, lone pair electrons, kind of scattering. So this one would look like, just for that chlorine atom, would look like this. So just for that chlorine atom, these are the 3 pairs of lone pair electrons. This is the sigma bond, this would be the oxygen atom. All right. So this, actually, I was glad that this one came up. This C2H4 is this one that I brought the other day. 2 carbons, and 4 hydrogens. So actually we said in this structure we have a double bond between the 2 carbons. So this is your sigma bond and this is your pi bond. So if we pick on either one of the carbons, because they're symmetrical, pick on the left one. So if you pick on that carbon, if we count sigma bonds, of course these are single bonds, are all sigma bonds. If you have a double bond, one of them is sigma, the other is pi. So I got 3 sigma bonds, no lone pair electrons. So 3 plus 0 is 3. So I'm back to that middle row. So what is its orbital hybridization? It is sp2. And then what's the geometry? Mm-hmm. It is trigonal planar. And then what's the bond angle? 120. Yep. Very good. Cool, cool, cool. And then this is, where'd you go? This is this one. Okay, so we have 2 carbons and 2 hydrogens and a triple bond between the carbons. So we have sigma bond, pi, and pi. So that's why it says, and we'll pick on the left one again, the left carbon. If we were to count sigma bonds, I got 1, 2. Because remember, if you have a triple bond, 1 is sigma and 2 are pi. So I only have 2 sigma bonds, no lone pair electrons. So I'm back to the first row. Okay, so what is its orbital hybridization? It is sp. What's its structural geometry? Linear, hot dog. And then what's its bond angle? Yep, 180. That's it. That's it. Very good. So now I need to kind of revisit this idea of not all bonds and lone pair electron domains, sigma bonds and lone pair electron domains, there's a little bit of a play in them, a little bit of a difference. The lone pair electrons actually are a little more voluminous, okay? So they take up a little more space than a sigma bond. But each one of these center atoms, so this carbon atom, this nitrogen atom, and this oxygen atom, each one of those, if you were to take them and evaluate them, you would come up with 3 plus 0, sorry, oops. You come up with 4 plus 0 for the methane. you would come up with 3 plus 1 for the ammonia, excuse me, you would come up with 2 plus 2 for the water. So in all cases, you're looking at sp3 orbital hybridization in all 3 cases. So you're thinking tetrahedral, and you're thinking 109.5 degrees. I almost said Celsius. 109.5 degrees. But and if you asked on a test, that's what you should say. But because the electrons take up a little extra space, they kind of squish down what's left. So only methane, this is the only one that has a bond angle of 109.5 degrees. These are always, they're going to be a little bit less than, oops, I put greater than, a little bit less than 109.5 degrees. And you would expect the water to be the least off because of the 2 lone pair electrons. So there's methane and tetrahedral, okay, 109.5 degrees. And here is ammonia. It doesn't have a bond angle. Hopefully I have it coming up. So that lone pair electron kind of squishes those hydrogens down. 2 lone pair electrons squish those hydrogens down even more. There. There's the bond angles. So the one that has the normal tetrahedral bond angle would be the one that has the 4 sigma bonds, the carbon with the singly bonded to 4 hydrogens. The other ones are less. So all right. So on your test, you're going to have a structure kind of like this, and I will ask you questions about atoms, okay? So, for instance, we're going to kind of go, I think, counterclockwise, starting with this carbon over here. And in this case, we're after structural geometry. So we're going to start with this one right here. But when I have to answer questions about this, what I actually do is first come up with hybridization. So, or just which row am I going to go with? So I'm looking at what, 4 sigma bonds, no lone pair electrons. So what would be the geometry there? Why would it be tetrahedral?
Because it's sp3.
Mm-hmm.
So
It's sp3.
Like the triangle with the top.
Yeah. It's trigonal planar because, and I think, I'll go back to what I said. I think that if you count 4, you should come up with sp3 hybridization. And that's, yeah, okay. Yeah, so that's tetrahedral. How about the nitrogen? What hybridization is it first? It is sp2. Perfect. No, it's not sp2. It's just simply sp. Yep. Yep. It's just sp. Do you buy that?
Yeah, I was doing the oxygen.
Okay. So if it is sp, then what shape is it? Linear. Yep. I'm liking it. Perfect. Now we'll scoot around to this carbon up here. What hybridization is it? That one's sp2. I'm liking it. So what's the shape? Trigonal planar. Very good. And last but not least, you have to point, we're going to take this little oxygen up here. So what orbital hybridization is it?
That's just sp2.
Yep, you both, yeah, sp2. Yep. And so what shape goes with sp2? Trigonal planar. Very good. So be able to do that, and then be able to do this. What's the bond angle? And we'll go kind of from left to right. But to me, to get to bond angle, I kind of go through, to get to the angle, I go through the orbital hybridization and the shape, and then I get to the angle. So the first one, actually, you guys told me that it was tetrahedral around that carbon atom. So what would be the bond angle for this? 109.5. Yep, I'm liking it. Very good. Oops. Okay, so scooting over, we did not evaluate this particular carbon. So what would be the orbital hybridization of that carbon atom? It is sp2. You got it. So if it's sp2, what bond angle are you looking at? Wait, if it's sp2, what shape is it? Trigonal planar, yep. And then the bond angle is 120. Perfect. You got it. And last but not least, we did the nitrogen but didn't do that carbon. So let's see, what is the orbital hybridization of that carbon atom? sp. Perfect. And so what shape is it? Linear. And then what's the bond angle? 180. Yep. So do you see where, I mean, this is a relatively complicated molecule. You can actually evaluate each atom for what its shape is, and then come up with what the shape of the molecule is. That's so cool. One thing I don't usually mention to my intro Gen Chem students, but is this idea of can, like if I have two atoms here, can the thing spin? Can it rotate? And actually, if you have only a single bond, this is my C2H6. Man, this thing can spin, this thing can rotate totally. And that's a player. But do you buy this, that actually there's no free rotation if you go ahead and go double or triple? It's stuck. It's stuck. But this can swing. That's kind of that's a player in the chemistry of molecules. So this is going to be due Monday, okay? So what we'll do, if I remember, is first thing on Friday, after you have your lab tomorrow, we'll kind of look at these. And I do want to go on into the next part. So it looks like this. This will actually help us for tomorrow's lab. So, resonance structures. Gotta love them. Resonance structures actually kind of... Do I have a definition of resonance structures, or I just jump into it? Is this my next slide? I just jump into it. Okay. It's coming up. The fifth slide is the definition. So it says something about resonance structures.
And there's a structure that differ only in the aspect.
Okay, only in the distribution of electrons. Distribution of electrons. So resonance structure. But resonance structures are, you're in the throes of making a Lewis structure, okay? And you come to a crossroads to give atoms a complete octet in your structure, and we're going to be doing this on Thursday. Bless you. And in your crossroads, you have a couple of options. Those are resonance structures. In your drawing Lewis structures, you can give them a complete octet this way, or you can give a complete octet this way. Those are resonance structures. So we're going to, and this is kind of the steps that we'll be doing in tomorrow's lab. So what if we had these four atoms joined together in this polyatomic ion? This is formate. This isn't one I don't think you had to memorize. But formate has one hydrogen, one carbon, and two oxygens, runs around with a -1 charge. We're going to draw this Lewis structure of the polyatomic ion. That's a polyatomic ion. So we need to come up with the pot of valence electrons, kind of like we've been doing. Okay, we have one hydrogen atom. It has one valence electron. 1 times 1 is 1. We have one carbon atom. It's a group 4A, so it has 4 valence electrons. We have 2 oxygens, and they are 6A. So 2 times 6, then they both bring a total of 12. And the fact that it's a minus or -1 means we have to kick in 1 charge. That's where that came from. So if you add them all up, you get 18. So you have 18 electrons. That's your pot. And what we're going to talk about tomorrow is the ones we're going to be working with is basically have an atom in the middle and bonds that connect them to other atoms. Okay, so an atom in the middle. Now the central atom needs to be the lowest electronegative atom. So you're looking for low electronegativity. And hydrogen never wants to be in the middle. So hydrogen never wants to be in the middle. That one's out. So electronegativity, you're going to have to remember how electronegativity varies. So we're going to put carbon or oxygen in the middle. We want low electronegativity. So electronegativity increases. They're both in the same period. So it increases from left to right. So which one's lower?
Carbon.
Yep, carbon, the one on the left. So we're going to put carbon in the middle. And so we have what I call a baby Lewis structure, a preliminary Lewis structure here. We're putting carbon in the middle, the lowest electronegativity. So we draw in the preliminary sigma bonds. So we got sigma bond, sigma bond, sigma bond. Now, the number of electrons we've used up here, how many electrons are represented here?
6.
Only 6, exactly. We have 2 here, 2 here, 2 here. We had a pot of 18, so 18 minus 6. So actually, I have 12 electrons to do something else with. And tomorrow I'm going to say the thing that you do with your leftovers after you draw your preliminary Lewis structure is you satisfy your terminal. So if carbon is in the middle, do you guys buy this? That the terminal ones are the 2 oxygen atoms. So you make your oxygen happy, and if you have leftovers, then you turn your attention to your carbon. So, oh my goodness. So those oxygen atoms, they only have 2. And if they want to have 8, they need to pick up 6. So that's why on the next page, what you're going to see is basically I'm going to take that 12 and I'm going to divvy it up. I'm going to put 6 there. I put 6 there. You're like, all right. So my pot's used up. My oxygens have a complete octet. And my hydrogen's wonderful with just a duet. But do you see where carbon's not done yet? Okay. So carbon's not happy. Carbon only has 6. Carbon needs 2 more. This is where you get resonance structures. In tomorrow's lab, this is step 5. You may or may not have to do step 5. It basically says, well, your terminal ones are fine. What about your central atom? It's not fine. So what we're going to do is we are going to convert. It's called converting. We're going to convert one lone pair electron. We're going to swing it in and make it actually into a pi bond. And in doing so, now if we do a little Venn diagram around carbon, it's got 8. So it looks like this. Okay, notice.
Does it matter what oxygen you do it to?
In this case, it doesn't because it's very symmetrical. Those oxygens are the same. But the point is you come up with 2 possibilities. You could take it from the north one or you could take it from the east one. Okay? So it's kind of up to you. Those are resonance structures. Those are resonance structures. So resonance structure that is a structures, Lewis structures that differ. They have the same pot of electrons. Each atom has a complete octet, but they differ only in the arrangement of the electrons. I call it swinging. I call that last step kind of swinging lone pair electrons in to make it a pi bond. So they only differ in what's been swung from where. Do you see they have their own little road now? Isn't that cool? It's kind of fun, the little... Getting closer. Okay.
It's gonna be there.
Either they have their own road. Well, no, that's hopefully the road to the new facility. That's true. Electron delocalization. I think this is so cool, too. Kind of has, when I think of electron delocalization, I think of the pi electrons. I went ahead and brought, fix it. I, over the years, have lost some of my. This actually is benzene. It's a benzene ring. Okay, so benzene has, it's C6H6. It's a ring, which means it's a circle that kind of connected. So here's our carbons, here's our C6, and they have sigma bonds, okay? And then these are our hydrogens. So each carbon is singly bonded to a hydrogen. So this is benzene. But the cool thing is it has alternating single, double, on a Lewis structure. So benzene on a Lewis structure would look like this. So C6H6. I used to be better at drawing these. So here's my carbon, here's my sigma bonds. Okay, kind of ugly. And they said each carbon has a hydrogen. Oops. And you'd be like, oh my gosh, that's not going to work because nobody has none of those have a complete octet, right? So here comes the pi bonds. So we could, if we call this carbon 1, carbon 2, etc. Between carbon 1 and 2, we could do double bond. And then we would do a single bond between 2 and 3. And then between 3 and 4, double bond. 4 and 5, single bond. 5 and 6, we do a double bond. Oops, my double bonds look like something else. So that's benzene. And around any carbon, if you want to kind of do the math, any carbon now has a complete octet. Okay, so it alternates. Talk resonance structures, we could go ahead and draw another benzene ring. Kind of running out of room. We could draw another benzene ring. Oops, other way. Down here. And it's going to show it in equilibrium. And this one would go carbon, 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 carbon. Oh gosh, that's terrible. And now instead of having a double bond between 1 and 2, we have a single bond. And we have a double bond between 2 and 3. Okay. So other than looking really ugly, those are resonance structures, and the electrons basically delocalize. And so when we talk about the reality of benzene, okay, benzene is neither the first one nor the second one. Actually, it's something kind of in between. So I don't know if this works for you, but rhinoceroses are kind of a combination or a hybrid of two mythical creatures. Then you have your rhinoceros. Okay? Kind of a strange analogy. So back to formate. So formate, we said, kind of the last step, step 5, when you want to give the carbon a complete octet, you can swing those lone pair electrons from either oxygen. It's totally great. Okay? And in reality, it's actually kind of an in-between of those two structures. Now, remember we talked about isotopes before? Isotopes are atoms of the same element that differ by the number of neutrons, so they have different masses. You can actually isotopically label your molecules so you know which atom is doing what. I think that is so cool. So in chemistry, when we say something kind of goes back and forth between two things, we use, instead of using a reaction hour kind of from left to right, and we'll be talking more about reactions, we basically say it goes from left to right and it goes from right back to left again. Two-way arrows. I was talking to my mom about that today. So are all possible Lewis structures that give all atoms a complete octet, do they make sense? Not necessarily. And I have an example coming up for you. So sometimes, in other words, you can draw a Lewis structure and you just looking at it, you're like, that Lewis structure gives everybody complete octet, uses the pot of valence electrons, but it doesn't make sense. But if you can get more than one reasonable resonance structure possibility of a molecule, it makes it more stable. So how do you know, and I'm going to show you an example, I'm going to pick on carbon dioxide, but how would you know if you drew a resonance structure that was illogical? Well, here are things to look for. You want to give everybody a complete octet, that's the first one. If you are going to have something that is partially negative, you want it to be on an electronegative atom. And you prefer not to have charge separations at all, though. So in tomorrow's lab, you're going to come to a crossroads. You need to give the central atom a complete octet. You need to say, well, which atom am I going to swing lone pair electrons from? Then you need to go back to what we said about the expected valence of the atoms. We said how many times does an atom want to reach out in a neutral molecule? We said 8 minus the group number. So I'll tell you which example that is in tomorrow's lab. But, okay, carbon dioxide. Positive valence electrons, okay, would give you 2, 4, 6, 8, 10, 12, 14, 16. 16 electrons you need to distribute around that molecule. And so these are both awesome. They use 16 electrons. They give the 2 oxygen atoms and the carbon atom a complete octet. How many people think the one on the left looks more reasonable? Why does it look more reasonable? It's more balanced. Exactly. The other thing is if you use the expected valence rules, so what I was just saying, carbon is a group 4A, so 8 minus 4, the expected valence is 4. Oxygen atoms are 6A, so 8 minus 6, the expected valence or reaching out is 2. So when I say reaching out, now we do count pi bonds. So we have sigma pi, sigma pi. Okay, so that's behaving. But if we look over here, this oxygen is reaching out once. It's not balanced, is it? And this oxygen is reaching out 3 times. So it's definitely not following the expected valence rules. So this one, dun dun dun, is also going to be due on Monday. So is that 3 assignments due Monday? Oh my gosh. So yeah, I'll try to kind of recap on Friday. All right then. Nothing due for Friday again. How do we do that? Anyway. Lots due Monday.